Cambridge International AS and A Levels Chemistry Paper 2 AS Level Structured Questions May June 2025 Paper 23 we're going to be solving today. Question number 1 states, the chemical properties of an element are related to the electronic configuration of its atoms. Okay. That simply means that the chemical behavior an element exhibits, that means the reactions an element shows, it's because of the electrons in the atoms. Electrons are transferred or shared during chemical properties. That's why chemical nature of any element, it's determined by the number of electrons it has, and the physical properties are determined by the mass number. That means the number of protons and neutrons in the nucleus. Always remember this. Give the full electronic configuration of a fluorine atom. To give the full electronic configuration means you cannot use this thing that AR this and then S2 or 2S2 or something like this. You cannot use this thing because this is shorthand electronic configuration. Full electronic configuration means you cannot use that noble gas. Going to the periodic table, where is fluorine? This is fluorine. It has 9 electrons. 9 electrons means that to fill 9 electrons, firstly it's going to be 1s2, then it's going to be 2s2, 4 electrons. We are done with 4 electrons, 2 electrons here, 2 electrons here, 1s2, 2s2, then it's going to be 2p6, 6, 7, 8, 9, 10. Now 2p6 means there are 10 electrons. We need 9 electrons, so it's going to be 2p5. 5, 6, 7, 8, 9. So that's the full electronic configuration of a fluorine atom. Next, reduce the number of pairs of electrons in the second energy shell N2 of an oxygen atom. Okay. The first thing you need to realize is that how many electrons oxygen has. Oxygen has 8 electrons. If it has 8 electrons, what's going to be the electronic configuration of oxygen? Oxygen is going to be 1s2, 2s2 and 2p4. Okay? Now they're talking about second energy shell, which means the quantum principal number you're talking is 2, which means we're only going to consider this and this subshell. We are not going to consider 1s. This 1s is not going to be considered. So now I'm going to draw the orbitals to make you realize the pair of electrons. This is 2s and this is 2p. 2p has 3 orbitals in it and 2s has 1 orbital. 1 orbital has 2 electrons and in 2p there are 1, 2, 3 and 4 electrons. Now you got to realize how many pairs you have here. See it for yourself. 1 pair in 2s and 1 pair in 2p. In total you only have 2 pairs of electrons in the second energy level. So we're going to write we only have 2 pairs of electrons. Draw the shape of the highest energy orbital that contains electrons in an atom of calcium. The highest energy orbital that contains electrons in an atom of calcium. For that, we need to write the full electronic configuration of calcium. Okay. Calcium has 20 electrons and 20 electrons, the electronic configuration for 20 electrons is 1s2, 2s2, 2p6, 6, 7, 8, 9, 10, 3s2, 3p6, 4s2. Now these are 20 electrons. You can count 2 plus 2, 4 plus 6, 10, then 6 plus 2 plus 2 again 10, 10 plus 10, 20. These are 20 electrons. So here's our nucleus, and you know that the as we go away from the nucleus, our energy level increases. So the furthest away from the nucleus, we have the 4s orbital. So it's going to be at the highest energy level. So the shape of the 4s orbital. You should know all s orbitals are spherical in shape. So you got to draw a sphere like this. That's going to be a 4s orbital. Write an equation to represent the first ionization energy of sulfur. Okay, the first ionization energy means that you have a sulfur atom, something like this, which is going to be in gaseous form, okay? And then what's going to happen is that you pluck out one electron from your sulfur atom and you make it a sulfur plus 1 ion, which is going to be in gaseous form, plus 1 electron that you plucked out of it. 1 electron that you are going to pluck out of your sulfur gaseous atom. These state symbols here are absolutely necessary for you to gain the marks. Next, explain why the first ionization energy of sulfur is less than the first ionization energy of phosphorus. So we're going to see this thing that sulfur is in group 6 while phosphorus is in group 5. But still, and you know that as this is group 15, this is group 16, phosphorus right here, sulfur is right here. As we move across a period, what happens to ionization energy is that it increases. But unfortunately, between group 15 and 16, the ionization energy across the period decreases. And the reason for that, the first ionization energy of sulfur is less. The reason for that is you're going to understand by drawing the electronic configurations. Okay? There is something that's called spin pair repulsion. I hope that you know it. If you don't even know it, you just have to realize this thing. This is your phosphorus, this is your sulfur. Phosphorus is going to be 1s2, okay? And then 2s2, 2p6, 2p6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This right here is sulfur. That's how sulfur should look. Not sulfur, this right here is phosphorus. That is how phosphorus should look as you move away from the nucleus. But if we talk about our sulfur, it's going to look similar, but there's going to be something different about it. I'm going to show it to you. This one right here, we can say is our sulfur. There's something different in sulfur and phosphorus. The difference is that sulfur has one more electron than phosphorus. The one electron is going to be accommodated here. Now you see that for the first ionization energy of phosphorus, I got to remove this electron. But for the first ionization of sulfur, I got to remove this electron. And you know that this electron is going to be removed more easily. Why more easily? Because it's facing spin pair repulsion from this fella right here. This guy right here is causing a spin pair repulsion on this electron that has to be removed. So there's going to be an ease in removing this electron. Okay? So you're going to write that the pair of electrons that are present in the 3p orbital of sulfur, they repel each other, which outweighs the effect of increased nuclear charge, because you know that despite sulfur having an increased nuclear charge, its ionization energy is less. That's what examiner is trying to ask us. So we're going to tell that the electrons in 3p orbital of sulfur have spin pair repulsion, and this word is very important in chemistry, outweighs, which outweighs the effect of increased nuclear charge. Arrange the three species F negative, neon and Na positive in order of increasing radius. To determine the radius, first we got to determine the ratio of protons and electrons. So if I talk about F negative. Fluorine has 9 electrons, but a negative means that now it has 10 electrons. So F negative, according to me, should have 10 electrons. Now if I talk about neon, neon simply has 10 electrons undisputedly, and the third is a sodium plus 1. Okay, a sodium has 11 electrons, but a positive one means it has lost 1 electron, so it's also going to have 10 electrons. So now I can see that all of my 3 species which I'm considering have 10 electrons. Now I got to consider the number of protons. Fluorine has 9 protons, neon has 10 protons, and my sodium positive one has 11 protons. Now you can see it for yourself. For the same number of electrons, my sodium has more protons. More protons means that it's going to pull these electrons harder towards the inside. The same number of electrons are going to be pulled by more number of electrons, and when they're going to be pulled inside, because this nucleus is going to be more positive, when they're going to be pulled inside by the protons, the atomic size or the atomic radii is going to shrink. So the smallest radius is going to be of Na positive, considering it has the highest number of protons. And then it's going to be my second number is going to be of my neon atom. Why? Because it has 10 protons. And the last, the biggest atomic radii is going to be of my fluoride ion, because it has the smallest number of protons. So it's going to be a fluoride ion. Done? Explain your answer. For the explanation, I'm going to write that F negative, Na positive, and neon all have 10 electrons. I'm just going to write whatever I did to find out the answer. Have 10 electrons. Okay. Na positive has 11 protons. Neon has 10 protons. Whatever I understand, I'm gonna write it down. And my F negative has 9 protons. I jotted down the proton number, the electron number, and I'm gonna explain. Na positive has the greatest proton number. Greatest proton number, in bracket I'm going to write nuclear charge, which means it's going to push the electrons with more force. So it's going to push the electrons or attract the electrons inwards. Okay? So more attraction, or you can say more electrostatic attraction, because between opposite charges you have electrostatic attraction between electrons and nuclei. Hence a bigger atomic size you're expecting. Okay? They all are isoelectronic. They have the same number of electrons, but the one that has the highest number of protons is going to be the smallest. Okay? Now we're going to write that attraction between electrons and nuclei greatest, so smallest atomic radii. Or you could give a reverse argument, which is that the fluoride has the fewer number of protons, so the largest atomic radii. For examiner to give you these 3 marks, first you have to tell all have the same number of electrons. Then you have to tell that either this or out of this, which of them it has the highest proton number, this one has the lowest proton number, that is why it has the largest radius, or this one has the highest proton number, that's why it has the smallest radius. So that's all. The chemical properties of oxides are related to the chemical bonding present in these compounds. These lines are like gems. the chemical properties of oxides like sodium oxide, potassium oxide, magnesium oxide, or sulfur dioxide are related to chemical bonding present in the oxides. Okay? Period 3 oxide produces a solution with a pH greater than 10 when it is added to water. State the formula of the oxides. So if you consider period 3, you have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. These are all the elements in period 3. Now you got to realize which oxide is going to give a pH greater than 10. Okay? So you have your sodium oxide, magnesium, aluminum. Aluminum is amphoteric, so cut it down. So it's going to react with both acids bases. pH greater than 10 means we're looking for a basic oxide. Okay? We need a basic oxide. This silicon, acidic, phosphorus, sulfur, these are all acidic oxides. Either it's sodium or magnesium that can give you a pH greater than 10. Out of these two, you have to be good with the chapter of periodicity. You have to learn the periodicity well. In the book, if you go with the periodicity chapter, you're going to realize that your sodium oxide, when dissolved in water, gives you sodium hydroxide, which has a pH of 14. And when you dissolve your magnesium in water, you get magnesium hydroxide and hydrogen gas, not hydrogen gas, only magnesium hydroxide, and it gives you a pH of 10. So magnesium is going to give you a pH of 10 dissolved in water, magnesium hydroxide, and sodium is going to give off 14. So pH greater than 10 will be of sodium oxide, and we have to state the formula of the oxide, so it's going to be Na2O. You got to learn this. All the oxides, you got to learn the pH that they're going to give when dissolved in water. Sodium 14, magnesium 10. Then aluminum is going to give you, it can react as both acid as well as base. And for other, you guys have to learn phosphoric acid and those sulfuric acid when the phosphorus and sulfur are going to dissolve. P4O10 is added to an excess of aqueous NaOH. Write an equation to describe the reaction. Okay, you have P4O10. First, you got to realize P4O10 is basically an oxide of phosphorus that's going to be acting as a acidic oxide. And since we know it's going to be acidic oxide and NaOH is a base, okay? So it's going to be an acid-base reaction that's going to happen between NaCl and our NaOH and our P4O10. First things first, you got to dissolve this in water to form an acid. So if we dissolve it in water, what kind of acid are we going to form? We're going to form H3PO4, which is phosphoric acid. Now this H3PO4 is basically going to react with my NaOH. Okay? You got to make sure that you basically add this in water to form this thing, and then this thing is going to react with your NaOH. So NaOH plus our P4O10, it's gonna give Na sodium phosphate PO4, but since this PO4 has a 3 negative charge, to balance it out there must be a 3 with sodium. So Na3PO4, this is the salt that's going to be formed, and we're going to form water. So always remember that whenever you have a basic oxide, this one right here is our basic oxide, and you make it react with a alkali, what do you form? You form salt and water, H2O. Now I guess this equation is not balanced. We need to balance it out. To balance it out, first things first, we got to put a 3 in front of sodium, because we need 3 sodiums right here. But when we put a 3 in front of sodium, something else gets unbalanced. 3 here. Now our oxygens, I guess, are not balanced, because we have a total of 10 plus 3, 13 oxygens on this side, and 5 oxygens on this side. So gotta balance the oxygens. And to balance out the oxygens, This is going to be a hit and trial method. So I need 2 minutes to balance it out. We have 4 phosphorus here and 1 phosphorus here. So let me put a 4 here. I'm going to do it with a different color. Balancing always takes me 2-3 minutes, so I'm going to chill and use my 2 minutes. 4 here. Now I have 12 NaOH, so 12 here. Now my hydrogens are 12, so a 6 here. Am I balanced? Yeah, I'm balanced. Chalo. Good to go. Table 2.1 shows the melting points of some oxides. We have sulfur dioxide, we have our water, we have SO3, we have SiO2, we have sodium oxide, we have magnesium oxide, and we have aluminum oxide. Identify the oxide from table 2.1 that contains the element with the highest oxidation number. Okay, so we're gonna start from the beginning. Okay, for over here the oxidation number of sulfur is a positive 4. Over here for hydrogen it's a positive 1. For sulfur over here it's a positive 6. For silicon over here it's a positive 4. For sodium over here it's a positive 1. For magnesium it's a positive 2. And for aluminum over here it's a positive 3. So the element that has the highest oxidation number is the sulfur in sulfur trioxide. So we're gonna put SO3 because we have to identify the oxide. A student suggests the following hypothesis. The melting point of an ionically bonded oxide is only determined by the chain charge on the cation. The melting point of an ionically bonded oxide is determined by the charge on the cation. Okay. Look, the charge over here is positive 1, over here it's positive 2, over here it's positive 3. From this to this there's an increase, but from this to this there's a decrease. So I don't think charge determines, because over here charge is increases. Okay, you can see that it's going from a positive 1 to a positive 2. Charge increases, but your melting point, it's also increasing. But over here the charge again increases. You can see from positive 2 you're going to a positive 3, but your melting point is decreasing. So use table 2.1 to deduce if this hypothesis is true or false if there is not enough information to make a conclusion. I'd say it's false. That's what I feel, because I just showed you that the charge over here is increasing but melting point increasing, but then the charge decreasing, melting point also decreasing. So I'd say it's false. It's false because from sodium oxide to magnesium oxide, the charge on cation is increasing and the melting point is also increasing. And I'm gonna tell the examiner whatever I think. Melting point is also increasing. But from magnesium oxide to aluminum oxide, charge on cation is increasing. Charge on cation, which is my aluminum, is increasing. But melting point is decreasing. You can see it for yourself. Melting point is decreasing, suggesting this hypothesis is false. Suggesting this hypothesis is false. That is whatever I think, and examiner is also giving you the marks for this. ठीक है? You just have to tell this thing. State why zinc oxide is described as a Bronsted-Lowry base when it's added to H2SO4. Asha, I'd be honest, I don't know the exact reaction that's happening over here, but I'm simply gonna tell the examiner it's acting as a Bronsted-Lowry base because I know Bronsted-Lowry bases are protons acceptors. So I'm simply gonna write it accepts a proton. Okay? So I'm gonna write that zinc oxide, I don't know the reaction, but I know that what's a Bronsted-Lowry base? It's a proton acceptor. And if the question states that this is acting as a Bronsted-Lowry base, then it must accept a proton. So it acts as a proton acceptor. That is what I think. Al2O3 is a white amphoteric compound. State the formula of aluminum containing species produced when Al2O3 reacts with NaOH. You should know that sodium NaAl 3 plus 1 plus O2. This thing can be formed. Okay? This thing can be formed. And there's another thing that forms that's common. This thing can form. Okay? But what we commonly form is not this. We form something else. We form NaAlOH4. Okay? That's what's going to form commonly. But this thing can also form. But we're going to write what forms most commonly, which is NaAlOH4. Okay? That is part of our syllabus. State the formula of the aluminum containing salt produced when Al2O3 reacts with H2SO4, which is, state the formula, aluminum sulfate. So Al2SO4 3. I hope you know how I got the formula. Aluminum has a 3 plus charge and sulfur has a 2 negative charge. So done. Different hydrocarbon mixture produced from the fractional distillation of crude oil have different uses. State the compound that is heated with long chain hydrocarbons to produce more useful smaller alkanes and alkenes. So what are they talking about? They're talking about a reaction that you call cracking. And for cracking, what kind of catalyst do you use? For cracking, you use an aluminum oxide catalyst. So Al2O3 is your catalyst which is used for your cracking. So they're talking about this compound. Describe how photochemical smog is produced during the combustion of petrol in an internal combustion engine. Okay, so over here what happens is that your nitrogen oxides and unburnt hydrocarbons, they are produced and they react together to form PAN. PAN is peroxyacetyl nitrate. Okay? Peroxyacetyl nitrate. Okay? So what happens is that you have to tell the examiner that your unburnt hydrocarbons that are produced react with oxides of nitrogen, react with oxides of nitrogen like NO or NO2 to form PAN, which is peroxyacetyl nitrate. That's a component of your photochemical smog. So what happens is this chemical basically causes your photochemical smog. C4 in the presence of sunlight, you can also tell this that they react. इस तरह बता सकते हो. C4H8 reacts with an excess of H2 to produce C4H10. You know what's happening over here, that this thing and this thing are reacting to produce a single product. So this is an addition reaction. Name the catalyst. Nickel catalyst is used in hydrogenation. Okay? This is hydrogenation, that a hydrogen is being added to an alkene. So hydrogen added to an alkene. So name the catalyst. It's nickel catalyst. Define activation energy. Minimum amount of energy that the reacting particles must have in order to react. Minimum amount of energy minimum amount of energy, or in simple words you can say minimum amount of energy that the colliding particles must have in order to react for a collision to be effective. For a collision to be effective, effective collisions are those in which your products are formed. So it's the minimum amount of energy that's required for a collision to be an effective collision. There are effective collisions and there are ineffective collisions. Ineffective collisions are basically when two of your reactants collide together and your product is not formed. And effective collisions is when they collide together, basically your product molecule is formed. When they collide with each other, something like this, they're going to collide ta. They're going to collide like ta. But what's going to happen is that no product is going to be formed because they collide with less energy. But when they collide with activation energy, that's a lot of energy, this product is going to be formed. Okay, the Boltzmann distribution for the reaction mixture of reaction 1 is shown in figure 3.1. Use the Boltzmann distribution to explain the effect of adding a catalyst on the rate of the reaction. Basically, if that's your activation energy right now, catalyst is going to move the activation energy towards the left and the activation energy is going to decrease. So we simply tell the examiner that activation energy decreases, hence more particles have energy equal to or greater than activation energy, hence more particles have energy equal to or greater than activation energy. So more effective collisions, hence the rate increases. And if we need to describe it in terms of the Boltzmann curve, because they've drawn the Boltzmann curve for us. So for that, we need to analyze what's going to happen to the curve. So basically, since the activation energy, initially I say it was this, but now it moved backwards to here. What happened is that the area under the Boltzmann curve of the particles that have energy equal to or greater than the activation energy increases. You got to tell the examiner this as well, that area under the curve with energy greater than EA increases. The reaction between sodium, sulfur, oxygen, whatever this is, and HCl is monitored at constant temperature. Okay, that's the reaction happening. These are the products forming. Figure 4.1 shows how the concentration of HCl varies with time. Okay, you gotta realize HCl is your reactant or your product. Okay, I know that this one right here, HCl, it's my reactant. Since HCl is my reactant and it's decreasing, okay, my reactant is decreasing, so I know that if it decreases faster, that means my reaction is going faster. If it decreases slower, that means my reaction is slower. And if the concentration of HCl becomes constant, that means my reaction is no longer happening. That's simple basic inference that I can make from the graph, knowing that it's telling me about the amount of HCl. Okay, use figure 4.1 to find the average rate of change of concentration of HCl in this reaction between 0 to 100 seconds and between 400 to 500 seconds. Include units in your answers. I need to find the average rate of change of concentration of HCl in this reaction between 0 to 100 seconds. Okay, let's go towards 0 seconds. On 0 seconds, my HCl concentration is 1. Okay? It's 1 mole per dm cube. At time 100 seconds, I'm gonna draw a straight line from time 100 seconds, something like this, and this is where I get it's 0.5 second. It's 0.5 mole per dm cube. So final minus initial. Final is 0.5 minus initial, or initial minus final, whatever. Minus 1.0 is 0.1 divided by time. Time was 100 seconds, so it's basically 0.5 divided by 100, and if I divide 0.5 by 100, what do I get? I move the decimal 2 places to the back and I get 0.005 0.005 mole per dm cube second. -1. How do I get this? Look. How do you figure out the units? What's the unit of concentration? The unit of concentration is mole per dm cube, and the unit for time is second. When this second comes up, it becomes mole per dm cube S-1. Okay? That's how you figure out the units. So mole per dm cube S-1. And over here as well, from 400 to 500 seconds. Okay, from 4 to 500 seconds, you can see it's 0. It's 0 because it's not changing. It's a flat line. So it's going to be a 0. 0 mole per dm cube S-1. Use figure 4.1 to identify the limiting reagent. Explain your answer. Use figure, which figure do I have to use? 4.1 to identify the limiting reagent. Okay, I need to use this figure and tell either HCl is my limiting reagent or Na2SO3 is my limiting reagent. Now look, at this flat line, the reaction is stopped. Okay? But, even the reaction is stopped, I have 0.1 mole per dm cube of my HCl left. HCl is still left. Though reaction is not happening, the line got flat, but HCl is still left. That means HCl is in excess. And since HCl is in excess, what is going to be my limiting reagent? Na2S2O3. Okay, that's how I figured it out. Don't miss out these important lines. This line told me that I had to look at the shape of the graph to identify what's my limiting reagent. So I need to explain my answer as well. So I'm going to tell Na2S2O3 is limiting reagent, and the explanation I'm going to give me, even when the reaction stopped, or no reaction is happening, still HCl is left. Okay? That's how I know. You can also tell about that HCl is left, and you can tell about the concentration that's left. Explain by the rate of the reaction changes with time. Always remember, whenever they tell that the rate of reaction changes with time, you have to tell that the concentration of your reactants is decreasing, so the frequency of effective collision is decreasing. Why? Because look, initially you have a lot of your reactants, but as the reaction proceeds, what happens is that the reactants collide and the reactants get used up. When the reactants get used up, what happens is the amount of reactants decreases. So what's happening is that when the amount of reactant is going to decrease, the frequency of the effective collision decreases because the concentration of reactants is continuously decreasing. So I'm going to write the concentration of the reactants HCl and Na2S2O3 is decreasing, so the frequency of effective collision is decreasing. Always remember this thing, that whenever you're going to do a reaction, over here it's a complex reaction, but even if as simple reaction like magnesium and chlorine, after some time this reaction is going to slow down. Why? Because your concentration of the reactant is going to decrease. The amount of magnesium you're going to take, if you have taken this much block of magnesium, after some time what's going to happen is that out of this much block, half of this block will be used up. Now only this much block is left. So what's happening is that the amount of your reactant is decreasing. So I'm going to tell the concentration of HCl and H2SO3 is decreasing. The concentration of the reactants is decreasing. So the rate is directly proportional to the frequency of effective collisions. Whenever they tell why rate increasing, frequency of effective collisions increases. Why rate decreasing, frequency of effective collision decreasing. Rate has a direct relation with frequency of effective collision. Whatever happens to the frequency of effective collisions, the same thing happens to the rate, because the rate of a reaction is because of the frequency of effective collision. So the frequency of effective collisions decreases. The reaction between Na2H2O3 and HCl is repeated in a second experiment. In the second experiment, this volume of this concentration reacts with this volume of HCl. Calculate the number of sulfur atoms produced. To calculate the number of sulfur atoms produced, first you have to look at the equation. This is sulfur. Okay? The simple ratio you need to do is, since you know that your HCl is in excess, you don't need to calculate its volume or moles or anything. You just have to see 1:1. So you calculate the moles of Na2H2O3, and then you know the moles of sulfur are going to be the same. So how do we calculate the moles of this? We multiply the volume, which is 25 upon 1000 times 0.05. (0.00125) मोल पर TM cube नहीं, सिर्फ मोल आएगा, because we're dealing with the moles. We have found out the moles. Now we know these are the same number of moles of sulfur, and in these many moles of sulfur, how many sulfur atoms are we going to have? In 1 mole of anything, we have Avogadro's constant number of atoms, 6.02 into 10 exponent 23. So in 0.00125 we have x. How do we find out the value of x? X is simply going to be 0.00125 multiplied by 6.02 into 10 exponent 23. Okay? You have your calculator, your scientific calculator, proper one. You're going to do the calculation and then you're going to get the answer. I don't have my calculator right now, so wait a sec. Let me do it. 0.00125 times 6.02 into 10 exponent 23, and that gives me, ओके तो अब आप लोग सोच रहे होंगे कि ये आंसर तो मार्किंग स्कीम से मैच ही नहीं कर रहा. दैट मीन्स दैट आई डोंट नो हाउ टू डू इट. यू आर राइट, दिस आंसर इज़ नॉट मैचिंग टू द मार्किंग स्कीम. बट क्या आपने फिगर आउट किया है? द थिंग इज़ दैट व्हेन एवर यू मेक मिस्टेक्स, द बिगेस्ट थिंग इज़ टू लर्न फ्रॉम द मिस्टेक्स. तो अब मैंने ये मिस्टेक की है यहाँ पे 2 मार्क्स की. आई डिड दिस मिस्टेक, ठीक है. इंटेंशनली अनइंटेंशनली छोड़ दें, आई वुड से अनइंटेंशनली. अच्छा, I did this mistake, but the thing is, did you guys learn from this mistake? I made a very common error. I would say that every person expect that 90% would make this error. When we are reading questions, we are just reading them like, acha yaar, let's just know what's happening and then just quickly try to solve it. We're not into what's happening. Over here, I even though highlighted the word in a second experiment, but I never realized this thing, that if the second experiment is happening, then I don't have to consider that my Na2 whatever this thing is was the limiting reactant in the first experiment. I need to now think in terms of the second experiment, that this fella can now be the excess reagent, can now be anything. The experiment I was looking before, I was keeping that thing in mind. Examiner is so clever, so clever, I would say. He just asked me this, over here, identify the limiting reactant. I identified, और जब भी we think about the limiting reactant, जो चीज़ हमारे दिमाग में आती है वो ये होती है कि if that thing is the limiting reactant, तो उसी से ही हमारे प्रोडक्ट के मोल्स डिटर्मिन होंगे. अगले में वो हमसे प्रोडक्ट के मोल्स पूछ रहे हैं. तो भाई this was a true gem question, I would say, in terms of if you want to check how vigilant was someone doing the paper. तो अब हम क्या करेंगे, अब हम सही आंसर इसका ज़रा फिगर आउट करते हैं कि क्या एग्ज़ामिनर ने हमारे साथ इसमें करने की कोशिश की है. अब जो उसने करने की कोशिश की है वो ये है कि उसने एक्सपेरिमेंट को ही बदल दिया. अब वो वाला एक्सपेरिमेंट नहीं है जो ऊपर हो रहा था. अच्छा, अब इस एक्सपेरिमेंट में हमारे पास ये जो हैं ये Na2S2O3 के वो है फिगर्स हैं. तो चलो इसके मोल्स फिगर आउट करते हैं. वो योगा के 25.0 अपॉन 1000 मल्टीप्लाइड बाय 0.050. इससे ज़रा n is my calculator. 25 divided by 1000 times 0.05, and that gives me 1.25 into 10 exponent negative 3. Now I need to find out कि HCl के कितने मोल्स हैं. ये आ गए मेरे Na2S2O3 के मोल्स. Now talking about the HCl moles, they are 0.0020 मोल्स के इसके हैं HCl के. Now I need to realize one thing. I need to look at the equation. 2 moles of HCl are gonna react with 1 mole of Na2H2O3. I need to figure out अब उन दोनों moles में से HCl limiting reactant है या Na2H2O3 limiting reactant है. To figure this out, अब इसके साथ HCl के इतने मोल्स के साथ इसके हाफ मोल्स रिएक्ट करने चाहिए. N2H2O3 के हाफ मोल्स रिएक्ट करने चाहिए बिकॉज HCl का रेशो 2 है और इस चीज़ का रेशो 1 है. तो इस चीज़ को हाफ करके मैं देखूँगी कि इसके कितने मोल्स रिएक्ट करेंगे. सो 0.0020 को मैं डिवाइड कर दूँगी 2 से एंड आई गेट 1 into 10 exponent negative 3. मतलब इतने मोल्स Na2S2O3 के यूज़ होंगे. बट मेरे पास कितने हैं, मेरे पास इतने मोल्स हैं. बट यूज़ कितने हो रहे हैं, इतने यूज़ हो रहे हैं. तो मतलब ये जो बाकी मोल्स हैं वो इसके एक्सेस में है. ठीक है, दैट वाज हाउ वी वर सपोज टू डू इट. ठीक है, इतने मोल्स हमारे पास इसके यूज़ होंगे बिकॉज मैंने HCl के मोल्स को डबल कर दिया और इतने मोल्स जो हैं वो मेरे पास एक्सेस में है. नाउ व्हाट आई एम गोना डू इज़, अब मुझे पता है ये इस मोल्स को देख के मैंने अपने सल्फ़र के मोल्स फिगर आउट करने हैं. अब HCl और सल्फ़र में क्या रेशो है, 2:1. यानी HCl के मोल्स को मैं डिवाइड करूँगी 2 से टू गेट द मोल्स ऑफ माई सल्फ़र. सो 0.002 divided by 2 and as expected I'm gonna get 0.001 moles आ गए मेरे पास of this sulfur. ठीक है, moles of sulfur. अब I know one thing. 1 mole में how many particles are there? Now I got to find the particles. 6.02 into 10 exponent 23. So 0.001 moles में कितने होंगे, x होंगे. बस आपने अपने आंसर को मल्टीप्लाई कर देना है 6.02 into 10 exponent 23 से और x की वैल्यू आ जाएगी 6.02 into 10 exponent 20. ठीक है, आपने बस क्या किया 0.01 को मल्टीप्लाई कर दिया 6.02 into 10 exponent 23 से टू फाइंड आउट द वैल्यू ऑफ x. ठीक है, that's how we did this question. Next question states, explain why the rate of the reaction cannot be monitored accurately by measuring the volume of SO2 produced in this reaction. Okay, so let's see. Okay, over here we have this thing, then we have HCl, then we have SO2 and then we have NaCl, S और H2. अब वो कह रहे हैं इफ़ वी मेजर, अभी हम देख रहे हैं अमाउंट ऑफ HCl दैट्स रिड्यूसिंग, बट वो कह रहे हैं नाउ यू गॉट अंडरस्टैंड कि SO2 को अगर हम मेजर करें मतलब हाउ इट्स डिक्रीजिंग, या मतलब वो तो प्रोड्यूस होएगी सो इट्स गोना इंक्रीज. सो हाउ मच अमाउंट ऑफ SO2 इज़ इंक्रीजिंग, अगर हम उसको मॉनिटर करें सो दैट कैन नॉट गिव मी परफेक्ट रेट ऑफ रिएक्शन. वाई? यू गॉट टू रियलाइज वन थिंग, इस रिएक्शन में क्या हो रहा है कि एसिड रिएक्ट करे इस चीज़ के साथ. SO2 भी एक acidic gas है. So there might be something that this SO2 might react समझ आई? Might react with something over here. और मैं एक और बात भी जानती हूँ कि यहाँ पे वाटर है, और वाटर और SO2 तो रिएक्ट करके सल्फ्यूरस एसिड नहीं बनाते थे. डोंट यू रिमेंबर H2SO3 सल्फ्यूरस एसिड वाटर SO2 का रिएक्शन होता था. सो ये जो भी प्रोड्यूस होगी वो सारी बाहर आएगी नहीं, वो कुछ वाटर से भी तो रिएक्ट करेगी. सो दैट्स व्हाट आई नीड टू रियलाइज कि रिएक्शन के प्रोडक्ट्स जो हैं वो आपस में भी रिएक्ट कर सकते हैं. सो SO2 प्रोड्यूस्ड में रिएक्ट विद वाटर, और जब वो वाटर के साथ रिएक्ट करेगी देन ऑब्वियसली आई कैन नॉट मेजर इट. Figure 4.2 shows the possible arrangement of outer shell electrons in one S2 molecule. Use figure 4.2 to predict the shape and the bond angle of the molecule of SO2. Shape is going to be non-linear. Why? Because this lone pair that's sitting on top is pressing down on this and this. So this is not exact 180-degree bond angle. This is not 180 degree. That's probably going to be less than 120. Okay, this is less than 120. So first things I'm going to write, it's non-linear. Non-linear. And if you want to visualize, then they've drawn it in a way that it looks 180 degree. But in reality, it's going to be something like that sulfur is going to be here. And this lone pair that's sitting on top is going to push the two oxygens downwards. So they're gonna be something like oxygen, oxygen, and now you're gonna have two pairs like this. 1, 2, 3, 4. Then there is 1, 2, 1, 2. Done. So it's going to be something like this. So that's a non-linear shape. You can think about it as like a water molecule shape. Acha. Now they're asking about the bond angle. How do we figure out the bond angle? For that, imagine कि यहाँ पे एक bond pair होता. अगर यहाँ पे एक bond pair होता lone pair की बजाय, for example एक और oxygen होता, तो ये bond angle कितना होता? You know, 3 bond pairs and no lone pair is going to give you an angle of 120 degrees. अगर यहाँ पे bond pair होता तो angle 120 degrees का होता है. Bond pair नहीं है, एक लोन पेयर है, तो एंगल इज़ गोना बी लेस देन 120. एक लोन पेयर से ऑलमोस्ट 2.5 डिग्रीज कम हो जाता है, ऑलमोस्ट, लाइक ऑलमोस्ट. तो आप इसको लिख सकते हैं 118 लिख दें या 117 लिख दें. आई एम गोना राइट 117 डिग्रीज. सो डन. आई एम गिवन विद electronegativity values of some elements, and what does the question say? Use figure 4.1 to predict the strength of the dipole moment in SO2 if any compared to H2O. Explain your answer. Oh, this one's a good question. The dipole moment in SO2 is gonna be less than H2O. You know why it's gonna be less than H2O? Because look, the electronegativity difference between hydrogen and oxygen is more. This means the lone pair is going to be more strongly attracted towards oxygen over here. But over here for sulfur, the difference is less. So the attraction over here is going to be a little weaker because both of them, sulfur, oxygen, both are going to attract. But over here, hydrogen is going to attract very less. So you're going to tell that there's going to be a weaker dipole moment over here in SO2. So can I tell the examiner weaker dipole moment in SO2 compared to water. Why? Because less electronegativity difference between sulfur and oxygen compared with hydrogen and oxygen, less. Next up we have W is a colorless liquid. Okay, we are now shifting towards organic chemistry, and over here they say W is a colorless liquid, and this is the formula for W. This formula reduced the empirical formula for W. I personally think that organic is hard work. Okay, I think because in organic you got to learn things, you got to learn the reactions. The people who are good at learning stuff, like rote learning stuff, they're good at organic chemistry because there's a lot you got to learn. So over here as well, it's all about like hard work. You got to figure out all the number of carbon atoms and then all the number of hydrogens over here. So I can see one carbon is this, uh, one carbon right here, and I can figure one carbon right here, and then I can see one carbon right here and one carbon right here. If I'm not wrong, then that is what I can see. So let me draw it something like I have a carbon here that's attached to OH, that's double bonded to an O, and then that's attached to another carbon that is double bonded to another carbon. This carbon right here is bonded to this carbon. I wish that I'm trying to draw it like the best way I can. Now I have to put in all the hydrogens to fill in all the valencies. 2 hydrogens here, and all the carbon balanced. 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4. So for me it's C4. I have 4 carbons. 1 2 3 4. Then it's O2, right? C4 O2, and H is gonna be 1 2 3 4 5 6, H6. So 2 1 times and 2 3 times. So this becomes C2 H3 and O. Okay? 2 different reagents are each added to separate samples of W as shown in table 5.1. Complete table 5.1. Okay. So for solid Na, I'm going to see some bubbles or effervescence or things like that. So I'm going to see some bubbles. The next part says Br2 in the absence of ultraviolet light. Now, the question is Br2, we know it's going to be used for testing alkenes, but why does the question says in the absence of UV light? Do you know why? To avoid free radical substitution in this compound. Always remember, free radical substitution doesn't always have in alkenes. Free radical substitution can have in any compound, like either be it a carboxylic acid or an alcohol. In the presence of UV light, free radical substitution can have even without breaking the double bond. But because over here we have, in the absence of double bond, we're doing it. So what's going to happen is that we're going to add this double bond is going to break from here. So what's going to happen is that this double bond is just going to get broken from here, and one bromine is going to be added at the top and one bromine at the bottom. And when this is going to happen, the color is going to change. The observation is that going to be that bromine, since it's orange brown in color. So what's going to happen is the color is going to change from orange brown to colorless, because this complex or this compound is going to be formed and this is colorless. Do you get what I'm trying to say? So we're going to say that color changes from orange brown to colorless. COLOURLESS. And the structural formula of the product, so we have to write the structural formula of this compound. So it's going to be CH2Br. I'm writing for this. Then it's going to be CBr bracket CH3, and then it's going to be COOH. Are you getting what I'm trying to do? Don't forget that this, we have considered this thing to be a branch. Why this thing is a branch? Because I cannot consider this thing as my branch, because there was a double bond here and there's a functional group, a halogenoalkane over here. I cannot consider this as my branch. You got to realize these small things while doing chemistry. So now this is the structural formula of the product. If you try to outsmart the examiner and draw this and think you're gonna get the mark. No, this is the displayed formula. For structural formula, you gotta give this thing. Okay. Figure 5.2 shows the two reactions of W to produce organic compounds Y and Z. Okay, so first reaction is that we are adding a reducing agent to it. So what was W? Let's draw it again. We have a carbon that is double bonded to O. Then we have an OH here that's bonded to another carbon that's double bonded to another carbon that's bonded to a CH3, and there's a CH2 here. Done. Okay, so now this compound, we're adding a reducing agent to it. You know, when we're going to add reducing agent, what's going to happen is that this functional group, this carbon oxygen functional group, this carboxylic functional group is going to be reduced, and this group is also going to be reduced. There's going to be oxygen added to it, and when we are adding something else, we are forming this thing. And what's this thing? We gotta draw it to figure out. We have a carbon double bonded to O, double bonded to an O, and this line represents there's another carbon here, something like this, and this carbon is double bonded to a carbon which is double bonded to another carbon and single bonded to another carbon. So this thing is converting to this thing. Potentially what's happening is, if you see it clearly, we had this, and now we're getting this straight line. Okay, reduce the number of sigma bonds and pi bonds present in Z. Okay, sigma bonds and pi bonds. For pi bonds, I would say this is one pi bond and this is the second pi bond. So there are two pi bonds. So for pi bond, I'm gonna say 2. And for sigma bonds, I would have to count. There's an H here, then an H here, then an H here, here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 sigma bonds I'm getting. So I'm gonna say 14. Okay, so now we're gonna reduce the structure. How are we gonna reduce the structure? Simply over here you can see a carboxylic acid group. This right here is your carboxylic acid group. When you add a reducing agent to a carboxylic acid, what does it convert into? It converts into a primary alcohol. So what's gonna happen is that this part is gonna be removed. Instead, 2 hydrogens are gonna be added over here and we're gonna form a primary alcohol. So the structure is gonna look all the way the same, something like this, but simply this OH is gonna remain here, and this carbon-carbon double bond for the carboxylic part is gonna be removed. So the structure of W is simply gonna be this structure. Identify the role of LiAlH4 when it reacts with W. Simple, it's a reducing agent. Even though we don't know with what thing it's reacting, but we know LiAlH4, lithium tetrahydride aluminate, is a very good reducing agent. So there suggests the reagent and the conditions required when W is converted to Z. Okay, so when W is being converted to Z, you gotta figure out what's happening. Look, W is an acid and Z feels like an ester. How do you convert an acid to an ester? You add an alcohol to it. And what kind of alcohol are you adding here? An alcohol that is 1 carbon. So what you're doing is that you're adding methanol to it. And you also know with methanol you add sulfuric acid, which acts as a catalyst for your esterification. So the conditions and the reagents. So the conditions are that you add H2SO4 that acts as catalyst, because that's an esterification reaction. And the second thing is, to make it, you add methanol to it. That's the alcohol used. I hope you get what's happening. Ester is being formed here. Figure 5.3 shows the structure of Z. Figure 5.4 is the infrared spectrum of Z. Okay, so there's an infrared spectrum, and over here we have to identify the groups, and over here we have the characteristic infrared absorption range in wave numbers over here. So the first is this CH, I guess we're talking about this one right here. This is the CH, which is an alkane. We're gonna look at all the dips that are happening. The first dip, that's A. Let's see where are we. So this feels something like here. Let's see, what are we talking about in A. It is before 2000, so it's gonna be an alkane. So since it's before 2000, it's gonna be an alkane. The next one, which is CH, B. B is somewhere here. So between A is somewhere here. A is somewhere here. Sorry. I just marked the wrong position. A is somewhere here. That's before 3000. B is somewhere here between 1500 and 2000. So let's see. Between 1500 and 2000, we have all this thing between 1500 and 2000. So it's C double bond O, or a amide carbonyl, or ester carbonyl carboxyl, or ester functional group containing the bond. But we're specifically over here talking about the ester bond, because this does not has amide or carbonyl or carboxyl. So we're talking about ester here. C double bond O. For C, let me draw a line here. For C, it's more inclined towards 1500. Okay? The line is more inclined towards 1500. If I draw it straight like this, it's messing up. But if I draw it straight, it's more towards 1500. This 1500, 1600, 1700, 1800. So it's more towards 1500. So for C, we are gonna be choosing this carbon-carbon double bond. Okay? It's an alkene, because I can see an alkene group here. So it's gonna be a carbon-carbon double bond. And for D, I can see my line is here. The dips we have to see. For D, it's simple that what are we looking for? It's 1000, 1100, 1200. So 1150. Definitely in this range, which is a C single bond O, which is a hydroxyl or ester part. So it's going to be C single bond O, since I know that over here I don't have any hydroxyl. I don't have hydroxyl. ठीक है, मेरे पास कोई hydroxyl नहीं है, तो फिर I'm gonna write it's ester. For here I'm gonna write alkene, and with that I'm done with the paper. I think I am. Oh, I'm not. Okay, Z is used to produce an addition polymer. Draw the repeat unit of the polymer. Okay, Z, where Z? This is Z. It's used to draw an addition polymer, and I have to draw a repeat unit of the polymer. Okay, first what I'm gonna do for you guys is I'm just gonna draw it. I've drawn it. Look, this is Z. I've drawn it. So I'm just gonna copy it, and then I'm gonna show you that how do I draw a addition polymer for this structure. So no, oh my god, what just happened? I reverse. Okay, good. No, paste. Yeah, so that's my structure. Now I need to draw the addition polymer for this structure. What do? I make my carbon-carbon double bond the center and everything above and below it. So carbon-carbon double bond should be my center. Above it I have this entire thing, which is COOCH3. Below it I have CH3, this CH3, above this I have a hydrogen, below it I have a hydrogen, something like this. I hope you're trying to get what I am drawing. So how do I draw a polymer for this? Is that I extend this something like this, and then these used to produce like this, and this part is going to be carbon, oxygen, double bond, oxygen, CH3. This part is going to be a CH3, and I'm done. This part has a hydrogen, this part has a hydrogen. To make it more accurate, I'm gonna move this entire thing backwards. Done. Something like this. Polyethene is an addition polymer made from ethene. Explain why ethene reacts with electrophiles but polyethene does not. Ethene contains a carbon-carbon double bond, a pi bond. Polyethene does not contain a pi bond. It reacts with electrophiles because the carbon-carbon double bond itself acts as a nucleophile because there is an electron cloud above and below it. So ethene has pi bond, which has a region of high electron density that's gonna act as an electron cloud above and below. So I'm gonna write that ethene has a pi bond which has an electron cloud surrounding it, while polyethene has all sigma bonds, while polyethene has all sigma bonds. HOCl reacts with this thing to produce this thing in an electrophilic reaction. Define addition reaction. The reaction in which only one product is formed is addition reaction. There is no rocket science in it. When two or more things are going to react to make only one product. Okay? So the thing is, two or more reactants, I would say, reactants react to form one, or you can say single product only. Single product only. Describe how Cl2 is used to produce HOCl. Make it react with water. So this thing reacts with water to produce this thing. I would just write water over here, and then you can say mix it with water, make it extract one use of HOCl. It's basically used as a sterilizing agent. The thing that you see in swimming pool, that chlorine that you can smell, it's because of this HOCl. So what state 1 use, it's basically a sterilizing agent, kill microbes or bacteria, you can say, in water. Then we have this that's moving on to this. We basically have to draw this reaction mechanism. Okay, so what's gonna happen first is that this electron cloud here is gonna attack this partial positive chlorine because it's more negative, and when it's gonna attack it, this bond is gonna break heterolytically and this OH negative is gonna take its electrons. Now we have an OH negative that has these 2 electrons. Now we form a carbon-carbon single bond, H, 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 and this Cl basically attaches here. Now we form a primary carbocation. We're going to form a carbocation here. This hydrogen is a cation now. Now this lone pair is going to attack this carbon. Yeah? This carbon, that's the cation. And now we're going to form this. So I guess that's all that we have to show because the lone pairs, the partial charges, they're already drawn. So I guess that's all. Okay, this thing reacts in a 2-step synthesis to produce this thing as shown in this. State the reagent and the conditions for step 1. Okay, we are adding a nitrile. Yeah, so the reagents and the conditions are going to be the conditions that we use to add a nitrile to a halogenoalkane. That is KCN in ethanol. KCN in ethanol. Identify the type of reaction that occurs in step 2. Acidic hydrolysis. Simple. This part being converted into a acid. So this is basically acid hydrolysis. That can happen with nitrile if you add acid to it. Complete the equation shown. Complete the equation shown to show reaction 2. Okay, so what you're gonna add is you're gonna add HCl to it in water, and you're gonna form this thing, HOCH2CH2COOH. This part converted into acid part, and the second thing you're going to form is all the products that's left, which is ammonium chloride. This Cl, this nitrogen reacts, this water provides the hydrogens, and you form ammonium chloride. So I guess that's all for today.